This is the fourth in a series of videos about colligative properties. This is a long section. In the last video, we talked about vapor pressure lowering, and now we're going to put that understanding into effect to talk about distillation and how we can separate volatile components. So first of all, we need to define the word volatile because you may not know what that means. So this property is called volatility. You probably see it on the safety warnings of some of the solvents you buy from the store. So volatility is the tendency of a substance to evaporate at around room temperature. So something that is volatile is going to evaporate easily. Something that's non-volatile is not going to evaporate from a liquid to a gas. Okay, so let's talk about solutions and the vapor pressure, starting with the picture we did at the beginning, and then indicating, how it would look different with a volatile or a non-volatile solute. So let's start with pure solvent. The solvent is always a liquid, and it is always a volatile liquid. Okay, so we are going to have a liquid. And so the liquid is going to be 100% solvent because there's just one thing, one liquid. And if this is a volatile solvent, some of it is going to volatilize into the gas phase, which means it is going to be 100% solvent in the vapor phase as well. So everything is solvent and all of the vapor is solvent. You see that shading in the video? You can't really see the shading in the video. Okay, we'll shade it a little bit darker. Is that better? Yes, I think it is. Perfect. Okay, so everything is red because there's only one component. So now let's try doing a mixture. We'll make it a non-volatile solute. It's being mixed. So this is like one of the examples up here. We like glycerin or glucose or sodium chloride, some sort of a solid that isn't going to vaporize and isn't going to contribute to the vapor phase. So here's my liquid vapor line. Let's say that we made a mixture of liquids and it was 90% solvent, so it could be water. And then we put in 10% of that non-volatile solute, some sort of a solid. We can shade most of this in red, and then we'll shade some of it in blue for the solute. Okay, so when we think about the liquid, this solution is going to be 90% one thing and 10% the other. What is the vapor phase going to look like? Because the solute is non-volatile, it isn't going to contribute to the gas phase at all. So just like the last picture, 100% of the gas phase is going to be solvent. It's all going to be the red piece. So that doesn't mean that the vapor pressure here is the same, right? We know that there should be a vapor pressure lowering whenever we add a solute. So the vapor pressure by itself is still going to be higher than the vapor pressure in the mixture, but there's going to be just one substance in the vapor. Okay, so now let's go even a step further and let's use a volatile solute. And once you start to have two volatile compounds, solvent and solute aren't super helpful anymore as terms. So let's just call this compound B, and we'll call the solvent compound A. And let's say in this picture that the volatility of compound A is greater than compound B. So we're going to make compound A the more volatile one. So here's our vapor liquid line. Let's say we made that same mixture as before, so 90% of one of the compounds and 10% of the other compound. Now, this picture is going to look different than the non-volatile. In the second picture, the non-volatile solute didn't contribute to the gas phase at all. In this case, because both of them are volatile, both of them are going to be present in the gas phase. But what we learn through Raoult's law is that the more volatile component, A, is going to make up a larger fraction of the vapor phase than the less volatile compound. So we're going to have 90% A and 10% B in the liquid phase. And in the gas phase, we're going to have 95% A and 10% B. So the more volatile compound A is going to make up a larger fraction of the vapor than the liquid, thanks to vapor pressure lowering. So let's make a note of that. The more volatile component, which was component A, makes up a larger fraction of the vapor than it does in the liquid. We increase the amount of the more volatile components in the vapor phase. And this is how we use distillation in real life, is we can heat a solution and we know that the upper part is going to be more concentrated in one of the pieces, and that's a factor we can use to separate two liquids from each other. We can use that difference in vapor pressure to separate them. So let's do an example to prove that point. So this example says the vapor pressure of pure benzene and pure toluene, which are two liquids at 25 degrees, are 95.1 and 28.4 millimeters of mercury. And let's say that our solution is 50% benzene by moles. What are the partial pressures above the solution? So we need to use Raoult's law. So we need to have the mole fraction of each piece, and we need to have the pressures of each of the pure pieces. So we have those here, pure benzene and pure toluene. And because this says 50% by moles, we also have the mole fraction. So the mole fraction of benzene is going to be 0.5 because it's 50%. And that means that the mole fraction of toluene is also going to be 0.5. So if we were to draw this in a flask like we did up here, I don't have quite as much space left, but I can make an extra long one. So in the liquid phase right now, we are 50% benzene and 50% toluene in the solution. Okay, so now let's look at what the partial pressures are in the vapor phase above the gas. So Raoult's law says that the partial pressure of benzene in a mixture equals the mole fraction of benzene in the liquid, which is 50%, times the partial pressure of benzene by itself, 95.1 millimeters of mercury. That should give 47.1. And then for the other one, the partial pressure of toluene in a mixture is the mole fraction of toluene in the liquid times the partial pressure of toluene by itself. And that's going to contribute 14.2 millimeters of mercury. All right, and we can already see a difference. We can already see this is no longer a 50-50 mixture in the vapor. There's definitely more of the benzene than there is of the toluene. So if we can quickly calculate the total here, total pressure, by adding these together, that'll give 61.3. And then if we want to take the fractions, if we want to take 47.1 divided by 61.3, that is going to give 77% benzene. And if we take 14.2 for the toluene and divide it by 61.3, the total, we're going to get 23% toluene. And that is the component of the vapor phase. So let's finish the picture. And we'll draw in the vapor liquid line. Maybe. There we go. Okay. So proof of concept, just like this picture that we drew up here with the volatile solute, down here when both benzene and toluene were volatile, we had 50% of each in a solution, but in the vapor phase, the more volatile piece, aka the one with the higher vapor pressure as a pure component, benzene at 95.1, the more volatile component makes up a larger fraction of the pressure, and the less volatile component, toluene at 28.4, makes up a smaller fraction of the vapor. So this might feel uncomfortable or confusing, so just sit with it and do a few examples and try and convince yourself that this is really a true phenomenon. And now I'm about to draw a truly horrendous picture of the distillation setup so that you know what it might look like in the laboratory if you were going to do this. So the process of distillation is the process of separating two volatile compounds. And we separate them based on their boiling point and their vapor pressure. So here's what your setup is going to look like. There is going to be a flask that you're going to start with. And that flask is called the still. And it's going to have your solution in the bottom. And it should have a stir bar, because otherwise you're going to burn your solution. So let's say this is our solution from the last picture. Let's say this is a benzene toluene mixture. Benzene toluene solution, even better. Solution of the two. So what we're going to do to separate them is we're going to use heat. This is supposed to be fire. Please don't laugh. We would probably not use fire. We would probably use a hot plate or some sort of an oil bath. Anyway, we're going to heat the solution until the solution starts to vaporize. And both components are going to vaporize, but the more volatile component, benzene, is going to vaporize in a larger fraction. So it's going to start increasing, and what we want to do is we want to start capturing this gas to separate. So we're going to put a nice long tube on the top, and that's going to help us to catch the vapor. It's going to have lots of little spots for condensation. And we're going to put a thermometer in the top for good measure. So we can measure the temperature. I don't know what this is called. We're going to call it a tube. Okay, so you're going to vaporize your solution. It's going to vaporize, and the vapor is going to go up, up, up into the tube, and it's going to cool as it gets farther away from the heat. And once it cools, it is going to turn into a liquid, and it is going to slide down the flask back into the solution. And what we want to do is we're going to try and capture some of that liquid sliding down the glass. When it slides down this side, we're hoping that it slides into this condenser tube. Maybe some of you have used one of these before in your high school. So here are some joints connecting those pieces of glassware together. This is called a condenser, or you might call it a water jacket, because this is a double-walled glass tube. The outside jacket is going to have holes for cold water to flow in and for slightly warmer water to flow out, and to keep this a nice cold flask, a good place for condensation. And on the inside is going to be a very poorly drawn tube where that steam is going to condense into a liquid, and the liquid is going to travel down the tube and be collected in a flask. There we are. So we're going to be collecting fluid at the bottom. This is called the receiving flask. There are going to be little drops of liquid coming down into the solution. And the solution at the bottom is going to be higher. It's going to be mostly that more volatile component. So it's going to be mostly benzene. If you want it to be 100% benzene, you have to repeat this process a few times. But we can definitely say that there is more benzene in here than there was in the first flask. Hope you appreciate my below average drawing skills of a distillation flask, but this is the reason we go to the trouble of doing all of this very complicated fractional math, is to figure out how to separate liquids in solution. This is a huge issue in industry and in medicine, being able to separate liquids from each other, and it's important that you know how this process works. In the next video, we will talk about freezing point depression and boiling point elevation, the last two colligative properties.